Good afternoon. My name is Daniel Kellaway, and this is my research. You may remember learning about divisibility in a previous class, but one rule remained elusive, the one for 7. And when you look at Google, it doesn't seem to be made much easier. It feels like you're dividing by 7 still, even though it's not quite that. So a simpler rule is taking, or a faster rule is taking groups of 6 digits together and adding them up, seeing if the result's divisible by 7. But turns out there's some type of rule like this for all primes, for each and every prime. The number may be different each time, but we have a rule. And so we have this group of n digits that we add up for the divisibility rule for some prime p. So we have base 10, but we could look at base 9. We could look at base 3. We could look at base 5. We could look at binary, base 2. So let's just generalize this and call our base b for base. So finding all these factors will give us divisibility rules. And the number of digits n is actually pretty important because that's what we're trying to look for in the end. So we have a name for this taken directly out of abstract algebra textbooks called the order. And here are some representations to give you an idea of what we're looking at. The foundational thought is b to the n minus 1 is a multiple of p. So with the discrete logarithm, we have instead of divisibility rules, we have a modular arithmetic algebra problem. And we're looking for n, which is the exponent. So we're taking some sort of a logarithm. The problem is this logarithm is very difficult to evaluate. It's the foundation for one of the cryptographic methods of today. We're going to look at the case where b to the n is congruent to 1 mod p. So now we have our base, our order n, and our prime p. So there are a lot of benefits to each of these different representations, a lot of different information that can be obtained. And because these different representations are just the same problem phrased in different language, we can get a lot of information that we might not get from just one of these. So we have cyclotomic polynomials. We're not going to evaluate these for the roots, but we will evaluate them at different bases to give us different function values. And we're going to take the nth cyclotomic polynomial where n is the order. But where's the prime come in? Well, we're testing to see if that function value of phi n to the evaluated at b is in fact divisible by that prime. So again, here are the representations of the problem we're looking at for finding the order. We investigated a few different areas like cyclotomic primes, the cyclotomic sieve. Here's the cyclotomic primes and the cyclotomic sieve in a table. We have the complex discrete logarithm problem. We have some applications. And we still have questions that we need to research. I thank you very much for listening to this presentation and have a good night.